Chapter 3, Functions and Graphs, Section 3.1, which is functions. We're going to determine whether a relation is a function, find the domain and range of a function, which we'll do more in a different video, and evaluate piecewise defined functions and greatest integer functions. Remember that a function consists of inputs called the domain and outputs called the range, and a rule by which each input determines one and only one output. So if we look at the examples of these two relations for a and b, we want to determine whether or not it's a function. For a, I know this is a function, and again, how do I know that? Because I have no repeating x values, or for every input there's one and only one output. For b, I know this is not a function because I have two of the same x values with different output values, so this is not a function. Now, let's go ahead and talk about evaluating functions, and again, you learned this in Algebra 2. So we want to find the indicated values of g of x is equal to root x squared plus 1. Now, remember that if you look at a, b, and c, you notice you have g of 3, g of negative 5, g of 0. Anytime you see that and you're given this right here, that's the rule that you're going to use. So again, I have g of 3, which means I have an x value of 3. I'm going to put 3 into my equation everywhere I see an x, and then simplify. So we have root 3 squared plus 1. 9 plus 1 would end up giving me 10. The square root of 10 does not simplify. If it did, I would, because remember 10 is just 2 times 5, which doesn't have any groups of 2 we can take out of the radical. For b, now you have to be careful because you have a negative. That's why anytime I plug things into my equation, I always put parentheses around what I'm substituting in. So negative 5 squared becomes positive 25 plus 1, which would give me root 26, which also does not simplify because it's 2 times 13. And for c, I have 0. 0 squared would just be 0 plus 1 is 1. The square root of 1 is just 1. Now, for these next examples, you're given f of x is equal to x squared minus x plus 2, and h is not equal to 0. Find each output. For this is the functions rule that we're going to use for each of these. I would pause the video, do it on your own, and then we'll just kind of check it together. For the first one that we have, we're plugging 2 into my equation. So everywhere I see an x, I'm going to replace that x with, in this case, a 2. And notice I always put parentheses around what I'm replacing x with. So 2 squared minus 2 plus 2 ends up giving me a value of 4. So f of 2 is equal to 4. And remember, that's an ordered pair. So really, if we were graphing this, it would be 2 comma 4 as a point. For b, we're plugging in 3, so I like to do, again, the same thing, so a parentheses around everything I'm plugging in for x. And now instead, this time I'm plugging in 3. So when I plug in 3, I simplify this, and I end up with 8. Now for the next one, notice that it says f of x. Well, that just means I'm plugging x in for x, which ends up giving me the original equation that we had, so the rule of the function, which was x squared minus x plus 2. For the next one, these are a little bit trickier because now we're not just plugging in numbers, we're plugging in more variables into our equation. So it's the same process, though, that we were doing before. Instead, we're just going to take out everywhere we see an x, we're going to put parentheses. And I'm making the parentheses a little bit larger this time because instead of plugging in a number, I'm plugging in x plus h. And then I would simplify. So for this problem, remember, anytime you have a binomial squared, you have to box or FOIL. So we have to FOIL this. So that would become x squared plus 2xh plus h squared. And then we have to distribute the negative here. So minus x minus h plus 2. Then you would look for to see if you can combine like terms, which we don't have any, so this would be my first equation. For my second equation, now we're doing the same thing, except for we're doing f of x plus h and then minus f of x. So we have two different functions that we're doing. So just like if instead I had f of 2 minus f of, what was it, 3? If we had this as our problem, well, you would plug 2 into the equation, which we already did, and we got 4, and then you would plug 3 in, which we already did, which we got 8, and then you would subtract the 2, so 4 minus 8 gives me negative 4. So that's basically the idea of what we're going to do here for E, except for instead of using numbers, we're going to be using variables. That's why it gets a little bit trickier when we start to get into more calculus kind of stuff. I'm just going to erase this so I can have room to write. So we already did f of x plus h here, so I'm just going to rewrite that. And now we're subtracting it from f of x, and notice I'm going to put this in parentheses. Why am I putting this in parentheses? Because if you don't put it in parentheses, you might forget to distribute that negative sign to each of those terms. So then I'm going to rewrite my equation, distributing the negative sign. Now I can look for like terms to combine. So x squared and negative x squared cancel out. I have negative x and positive x, which cancels out. And I also have 2 and negative 2, which ends up canceling out. So for this problem, notice that I am left with 2x h plus h squared minus h, and nothing simplifies any further, so this would be my solution. Now, why did we do that whole long process? So again, I started with numbers just to show you that something that's familiar to you. Now, instead of using numbers, we're going to be using variables to plug into a function. And why do we do that? Because it's the function, if we do this right here, this is called the difference quotient. And the difference quotient plays a really important role in calculus. So for this, notice that this, you have to, in order to be able to use the difference quotient, you have to be given the rule for the function first. So this was what we were using. Now, basically, I'm taking this rule and I'm going to be computing f of x plus h minus f of x over h. So notice that anywhere I have an f in parentheses, that's stuff you're plugging into your function. Notice that this h right here does not have an h of x or h of anything, so that's not really function notation. That's just a variable in the equation that you're using to compute the difference quotient. So for this, we have f of x plus h minus f of x all over h. Now, if you look above to what we did all of that. We just did that for problem E that we have right here. So I'm just going to go ahead and write that up here. So 2xh plus h squared minus h. And then again, this is just a variable. We're not plugging anything in for it, so it would be all over h. So the next thing that I would want to do is simplify. So in the numerator, I can factor out h. So then when I do that, I get 2x plus h minus 1. I need that placeholder over h. Notice your h's cancel out, so I'm left with 2x plus h minus 1. Now, let's go back a minute and kind of let's talk about, well, what is this difference quotient? Why are we trying to find it? Well, the difference quotient is the bridge between algebra, which is kind of calculating the slope, and calculus, which is the derivative. And you're saying, okay, well, what is a derivative? A derivative is how fast something is changing. So for the difference quotient, it measures the rate of change on a curve at any point. And we can geometrically do this by using secant lines or tangent lines, but it's pretty cool that, you know, instead of just having something that's a straight line and finding the slope, now we can say, well, if I have any kind of curve, I can find the slope of the line using this difference quotient. And again, it's very important to calculus. So those of you who are moving on to calculus, you want to make sure you know how to do this. Now, let's talk about where that difference quotient function comes from. So remember, it was, we just said f of x plus h minus f of x all over h. And of course, you have to be given some kind of function first, like f of x equals x squared. So the way where this comes from and where we get that is if you think about a line, and I'm not going to draw a straight line, I'm using a curve because we use the difference quotient because it helps us find the slope or the rate of change, I should say, at any given point on a curve. And in this case, so we're going to compute the slope of a secant line through 2 points on a graph. So let's pick out 2 points that we have. So we have one right here, and let's use this one right here. Now, instead of calling this point 2, I'm just going to use variables for our sake. So I'm going to call that x. And this function, or the curve that we have, I'm going to say that this curve I'm going to call f of x. So if I have the point x right here, then what is the y coordinate? Well, it would just be y, but in our case, we're going to use our function notation. So I'm going to call this point right here x comma, and then f of x. Because remember, f of x is just function notation, so that just means the y. So we have x comma y. Now we're going to have this other point, which is right here. We can't call this x because we've moved over some amount. How much did we move over? So we moved over x plus a little bit more. So we're just going to call this x plus h because that's what we use in the difference quotient. And so this point right here would be x plus h comma, well, how do you find the y coordinate? You would plug that into your function. So we don't know what the function is. We only know that we have f of x, so we're going to do f of x plus h. Now, again, for this, basically what we're going to be doing is it computes the slope of the secant line through the 2 points of the graph to help us figure out what the rate of change is. So I went ahead and drew in the secant line, which is that dotted green line, and so now we're finding the slope that goes through those 2 points. Well, we have the 2 points. Remember, how do you find slope? y2 minus y1 over x2 minus x1, but in this case, we're using x plus h and f of x plus h and x and f of x. So if I want to find the slope through those 2 points, we would just use our formula. So I have f of x plus h because that's my y2 coordinate, and this would have been my y1 coordinate, so minus f of x all over, now this is my x2 and this is x1, so then this would be x plus h minus x, and notice when we simplify this, I get f of x plus h minus f of x all over h. So that, again, is just calculating the slope of a curve through 2 given points. And in calculus, what we try to do is we make those points closer and closer and closer together until we get a tangent line, so that, again, we can find the rate of change at any point on a curve. And it's, like I said, again, pretty cool that we can, go ahead and do that. So the important things to remember is that you have to be given some kind of function f of x, and you're going to be using this right here, plugging in x plus h and then subtracting the original function all over h. And again, notice this is just a variable in the equation when we have h right there. So let's go ahead and practice these. So for each of these, we are going to compute and simplify the different quotient given. For the first one, we have 3x plus 1. So first of all, I would write down my difference quotient. So we get f of x plus h minus f of x all over h. So again, we have the 4, which is right here. Now we're plugging in, instead of plugging in numbers, we're plugging in variables. So we showed before, if I were to do f of 2 minus f of 3 over h, what would you do? You would plug 2 into the equation, then you would plug 3 into the equation, subtract the 2, and divide by h. But instead, we're not using numbers, we're using variables. So for the first part, I have my equation, we're doing f of x plus h. So if it helps to do them separately, you can. So this is what I'm going to do first. So f of x plus h would mean we are plugging in everywhere we see an x, we're going to plug in x plus h. So that goes in here. And now I simplify. So I get 3x plus 3h plus 1. Now we know that f of x is equal to just the original function. And then we're going to divide all of that by h. So that you take your 2 equations. So 3x plus 3h plus 1 minus your original function, 3x plus 1. Don't forget to put it in parentheses, all over h. And then the next step would be to just distribute and combine like terms. So 3x plus 3h plus 1 minus 3x minus 1 all over h. Combine like terms. Notice that I have the 3x, and the negative 3x cancels out, 1 and negative 1 cancels out, and I am left with 3h over h, which cancels out to leave me with 3. Now, if we think about, again, what the difference quotient is doing, it's computing the slope of the line through at any point, any given point that we have. So if you look back at this line, this is just a something that's linear. So we know how to find the slope of something that's linear because remember y equals mx plus b. Now if you look at that, you have 3x plus 1. So it makes sense that our solution would be 3 because the slope of the entire line is 3. So no matter what x value you pick, the slope at any given point on the line would always be 3. Now it's a little bit harder to do these problems when you have something that's not just linear, when you have things that are quadratic or cubic, etc. That's why we do the difference quotient. So even if the equation is linear and it asks you to compute the difference quotient, you still need to show all of that work. Now, if we look at B here, we're going to do something that's a little bit harder. So again, we're computing the difference quotient for this equation. Now, I always like to write down the difference quotient. Then the next part would be to do f of x plus h. I like to do them separately. You could do it all in the same equation if you wanted to. This just helps me when I do it separately to keep everything in order for me. Now, first things first, everywhere I see an x, so I'm going to take out my x's in my equation, and we're plugging in x plus h. Just like if I had f of 2, everywhere I saw an x, I would plug in 2. Then I need to simplify. If you have a binomial squared, you have to FOIL or box it out. So we get here x squared plus 2xh plus h squared plus x plus h. Now look to combine like terms, which you don't have any. And our original function f of x was equal to x squared plus x. So now I'm going to take those two, subtract them, and divide by h. So we have x squared plus 2xh plus h squared plus x plus h minus my f of x, which is x squared plus x, all over h. Don't forget to put the second part in parentheses so you can distribute that negative. So x squared plus 2xh plus h squared plus h minus x squared minus x all over h. Then if I combine my like terms, I have x and negative x. I also have x squared and negative x squared here. And I think that's all we got for like terms. Now I can go ahead and continue to simplify this. We get 2xh plus h squared plus h all over h. Now I can simplify this still further because notice in my numerator I have h with every term, so that means I can factor out a h. If it wasn't in every term, I could not do this. So I have h, take that out. Don't forget your placeholder. H over h is just 1, and notice I'm left with 2x plus h plus 1. So this equation, using the difference quotient, will help me find the slope of the line at any given point given this equation. Now, we're not going to actually do that part just yet. We're just concerned with seeing if we can actually find the equation that's going to help us find that rate of change at any given point on our curve. Now, the next problem, or number 3, or this last one right here, I want you guys to do on your own, and then we'll go over that in class together. All right, for the next part, functions defined by equations. Equations in two variables can be used to define functions. However, not every equation in two variables represents a function. So, for example, we want to determine whether each function defines y as a function of x. So if it defines y as a function of x, that means we want to solve for y to look at our equation. And let's do this without our calculator. So without our calculator, what I would do is I would subtract x squared from both sides. I would get y squared is equal to negative x squared plus 16. And then remember, if we want to solve for y, if it's being squared, you have to take the square root of both sides. And anytime you get rid of an even power, you have to remember the plus or minus. Now, because of that plus or minus that I have right there, that means we're going to have, for every x value we put in there, you're going to have two output values. So because of that, I know that this is not a function. And again, it's because of that plus or minus, we have two output values. And if you were to graph this, you notice that it would look like a sideways parabola. So that would not pass the vertical line test graphically. Now, if we look at B here, if we want to determine if y is a function of x, same thing you have to solve. So if you look at this one, I have that y squared again. So if I take the square root of both sides, y equals plus or minus the square root of 4x plus 1. Because of this right here, for every x value, I'm going to have two y values. So this is also not a function. If you look at C here, now it's already solved for y for us. If I look at this, I have 4x squared plus 1. If you graph that, you know it's going to be a parabola because it's a quadratic equation, which does pass the vertical line test. So yes, this is a function of x. And the next one, if you look at it, now we have y to the fourth minus 4x equals 1. So solve for y to the fourth by adding the 4x to the other side. Now, again, to get rid of an even power, you have to take the now fourth root of both sides and plus or minus your solution. So plus or minus the fourth root of 4x plus 1. And again, because of this plus or minus, for every input that we have, we're going to have two output values. So this is not a function. Basically, when you're doing these kinds of problems, they're pretty simple because when it asks if y is a function of x, you just have to look to see, is the y to an even power? Do you have any y's to an even power? We're going to have to take the square root and have two output values. And of course, you can always graph it on your calculator, and you can look to see, does it pass the vertical line test? And let's just really quickly graph the first one. And I'm sorry because looking at this, I said it was a sideways parabola. This is obviously not a parabola. If you remember from Algebra 2, this is actually a circle because we have an x squared and a y squared. So if I put this in my calculator, remember we don't have plus or minus that we can put in, so you have to put in one with the positive radical and one with the negative in front. And remember to use the negative sign, not the minus sign, when you're putting that negative in front. If I graph this by hitting zoom 6, notice that doesn't look like a circle, because remember when we're doing these, you want to hit zoom square, which makes it look more like a circle. And if you look at this graph right here, of course, this would not pass the vertical line test, which is why it's not a function. So let's go ahead and do this last problem, and that will be it for these video notes. We're going to do this application. It says, Robin cleans small passenger airplane interiors at an airport. At most, she can clean 24 airplanes per month. Robin pays a license fee of $150 per month to the airport. Her cost per plane is approximately $82.50. She charges $229 to clean each plane. Let X represent the number of planes she can clean a month. So the first one says we want to express Robin's monthly revenue R as a function of X. So I would maybe pause this and try to see if you can do it on your own. If we're trying to express Robin's monthly revenue R as a function of X, then of course we're going to do R of X. So we would get R of X is equal to, well, the revenue is how much we're making. So if you look here, it says that for this, she charges $229 to clean each plane. So 229 times X, because X stands for the number of planes that she's going to clean per month. So then for B, it says express the monthly cost as a function of X. So now we're going to do C of X for this one. Now the cost for this says that we're going to pay a license fee of $150 per month, and then also it's to clean each plane, it's $82.50 per each plane, so 82.50x plus 150 to pay for the license fee. Then it says we want to find a rule and the domain of the monthly profit function. So for this, we have the rule is going to be, of course, your profit, P of X, is going to be equal to how much you're making, so R of X times minus your cost. So in this case, the profit is equal to 229x minus the cost. I'm going to put it in parentheses because we're going to have to distribute that negative. And then, of course, you would just want to go ahead and simplify this. So your profit function is equal to distribute the negative and combine like terms. So we have negative 150, or you would see the x's first, so 146.50x minus 150. So this right here would be my profit function. Now for this, the domain cannot be all real numbers because in this case, if you think about an airplane, can an airplane have, can you have negative airplanes? No. So that means I know I'm going to start with 0 and I'm including 0 because we can clean no planes a month. And then it says that at most she can clean 24 airplanes per month. So comma 24. So this would be the domain. And of course, I put that in interval notation. Remember, the brackets mean we're including 0 and 24. So make sure you bring this with you to class. We'll talk about piecewise defined functions and domain on a different video, but we'll need this in order to do what we're doing in class tomorrow.